In an earlier video, I talked briefly about this RF demo board for the Nano VNA. At the time, I didn't talk very much about the connectors that are used on this board, so I thought it might be a good idea to talk about those, but to expand the subject to include RF connectors in general, which I've touched on a few places, but what I'm going to be trying to do here is to give you a kind of overview of a limited area. Specifically, I'm going to be talking about 50 ohm coaxial RF connectors. Now, we're not going to talk about connectors for 75 ohm like are used in the cable industry, although some of these connectors are available in 75 ohm, nor connectors for things like twin lead and biaxial and all the other kinds of, but basically 50 ohm coaxial RF connectors. We're going to start by looking at one of the earliest coaxial connectors called the UHF connector, which actually goes back to the 1930s. And in each case, what I will do is show you an example of these particular connectors. We're going to talk about others as well, including the N connector, the BNC connector, the TNC connector, and then get into some of the more modern, and by modern, a lot of these go back to the 60s, but still, things like SMA, SMB, and SMC connectors, and then some of the newer micro-miniature coax connectors, like the MMCX, which was actually developed to a European standard, and the AMMC, also sometimes called the U.FL, which is a micro-miniature coax that was actually preceded the MMCX by a little bit. This one was actually developed in '91, and the company and it was patented, and the company that the patent was assigned to allowed the patent to lapse by failing to pay the maintenance fees. I think that was in 2001 or 2002. Anyway, it's been more than 10 years ago since they allowed the patent to expire, and as a result, a number of other companies, including Amphenol, UFL is the designation that the original company used for this. I do not know what UFL stands for. I've been told the U stands for ultra, but nobody seems to know what the FL means. If you do, you might put a comment in this video. But recently, Amphenol has begun making a micro-miniature coax, which is identical to the UFL. It mates with it and everything, that they call the AMMC, and I'm going to talk about that in part so that you won't confuse it with the MMCX. They are different. And finally, we'll talk about some of the variations. For example, the fact that some of these come in reverse polarity, some of them come with left-hand threads, some of them are intended to be hand-tightened, and some are intended to be tightened with a torque wrench. So if that looks interesting to you, stay tuned. So the first connector we're going to be talking about is known as a UHF connector. It was developed as a shielded banana plug connector. The center pin of a UHF connector is actually the same size as a banana plug, and the case, that is the barrel and the threaded portion are actually come from an Amphenol microphone connector design, which was actually used in the early days for some RF. In fact, a lot of test equipment built during and a little before and a little after the war had Amphenol connectors instead of UHF connectors. They're not very good RF connectors, and I'm not going to cover them here, but they are part of the history behind the UHF connector. This is the plug, often called the PL259, and this is the socket, sometimes referred to as the SO239. SO, of course, for socket, PL for plug. So that's the UHF connector. It generally is good up to anywhere between 100 and 300 megahertz. It was developed in the 1930s, and really well-made ones will actually work up to about 500 megahertz, but most of the ones you find, I wouldn't use much above 100 or 150 megahertz. The next kind of connector that I wanted to talk about is the N connector. Now, this connector was developed by a person at Bell Labs named Paul Neal, and it was developed in the 1940s and was originally used on a lot of the military radar equipment that was also developed in the 1940s. Some people, because it was used a lot on Navy ships, think that the N stands for Naval Connector, but actually it stands for Neal Connector. Later, this was further developed and has now been extended to work up into the many gigahertz range. Originally, it only had to work into the lower gigahertz range for microwave or millimeter waves, but today, many of these N connectors work at 11 gigahertz or more. Now, this particular design, and many others, are a part of Mill Standard 348. And what you'll find is that Mill Standard 348 is used for the N connector, the BNC connector, the TNC connector, and many of the SM connectors, SMA, B, and C. So if you want to know the actual specifications of these connectors, look for Mill Standard 348 online. This particular connector is an adapter that will go from an N connector to a UHF connector. Now, UHF connectors are often used on, and pardon the motion here, on equipment like that spectrum analyzer. That's a Rigol DSA 815. Over to the left, you will see an Instec, and further to the left there is a Siglant. All of those are spectrum analyzers that go up to, in the case of the last two, 3.5 or 3 gigahertz or more, and in the case of the first one, the Rigol, 1.5 gigahertz. And notice they all use N connectors for their attachment to the circuit. Here is an N socket that the N connector or N plug mates with. Notice that unlike the UHF connector, the pin in the center itself has a hole in it, and that allows it to maybe I should put it another way. The impedances of an N connector are very carefully controlled. A UHF connector, some of them that are well made, have fairly controlled impedances, but many of them do not. But an N connector has a very carefully controlled impedance. And this is an adapter that will go from an N to a UHF. In other words, on this end is what is called a PL259. Next, let's talk about the BNC connector. Now, BNC stands for Bayonet Neal Consolman. And some people think that it stands for Bayonet N Connector. And if you want to think of it that way, that's fine too, because that's what it is. It is basically the same controlled impedance of an N connector, but in a slightly smaller form factor and with a bayonet connector. And if you've ever served in the infantry, you know that this is the way a bayonet attaches to a military rifle. At least American bayonets do that way. You put it on the end of the barrel and then you twist it to hold the bayonet in place. And of course, this was developed shortly after the war to replace end connectors in certain applications where they wanted or needed something smaller than a traditional end connector. This is the male, and generally in connectors, the male or female is denoted by what the most central connection is. In this case, it is a pin. Therefore, this is called a male connector. And on this side, since the center is female, this would be called a female BNC connector. And as you see, it has the little tabs on the side that allow the bayonet to attach when it's rotated. So this is a BNC to BNC adapter. BNC generally work up to about 4 gigahertz if they're well made. There are some that don't even work up to that level, especially some of the cheap ones that you buy, imports that you buy on eBay and places like that. But if you buy a quality BNC connector, you should be able to rely on it up to about 4 gigahertz. This is an SMA connector, and SMA stands for Subminiature Type A. It was developed in the 1960s, and well-made SMA connectors work up to about 18 gigahertz. Now you may notice that this has a pin in the center, so this is a male SMA connector. The reverse side is a female SMA connector. Notice the center is a female. So this would be called a normal polarity connector. Now normally, if the inner thread is mated with or matched with a male center pin, that is the traditional SMA connector, and the SMA socket is generally an exterior thread with a female center. There are SMAs that have reverse polarity. For example, this one, you notice that the outer thread is mated with an inner male pin. I hope you can see that. It's a little hard to see at this distance. But this would be a reverse polarity SMA, and you may find reverse polarity SMAs on a lot of routers and other Wi-Fi equipment. The reason for that is because the FCC was concerned in the early days of Wi-Fi that people would attach antennas with more gain than the FCC wanted to see, and so they required Wi-Fi manufacturers to use a connector that the FCC considered was not readily available. Well, of course, it didn't take long until lots of people were making reverse polarity SMA connectors and antennas with reverse polarity. And so, like anything, when you try to stop people from doing something, you invariably encourage them to do it. And that's what happened in this case. So today, even though the FCC no longer is pushing router manufacturers to use reverse polarity connectors, that has become such a standard that most routers today have reverse polarity antenna connectors. In addition to the Type A subminiature, there also is a Type B called an SMB, and a Type C called an SMC. Once again, these are all a part of Mill Standard 348. The SMA, as I point out, well-made SMAs will go to about 18 gigahertz. The SMB to about 4 gigahertz, and the SMC to about 10 gigahertz. Now, the reason that they are different is they have different specifications, and they are built to different tolerances and standards. The numbers that I use for these frequencies, these upper frequencies, and the reason that I have an approximation sign in front of all of them is that the actual figure varies. There are some SMA connectors that will go above 18 gigahertz, and there are some that won't even come close to 18 gigahertz. Same is true of Bs and Cs. So I realize now that I also forgot one. I haven't yet talked about the TNC, or the threaded Neal Conselman, which works up to about 11 gigahertz. It was developed in the 1950s, in other words, after the BNC, and the reason is it was thought that a threaded version of the smaller Neal Conselman, or N connectors, was needed. Once again, this is part of Mill Standard 348, and this was developed in the 1950s. In fact, I think it was developed in 1954. It might have been a little earlier than that. But let's take a look at a TNC connector. So here is a TNC, or threaded N connector, although it's actually a threaded BNC connector because it's on the BNC form factor. And notice this one is threaded on one end and it has a BNC on the other. So this is a TNC to BNC adapter. Now, as I pointed out, these were developed in part because a threaded connector, like the N connector, actually is better, the impedance is easier to control, and the TNC will actually go, well-made ones, up to about 11 gigahertz. So this will actually work at the same frequencies as an N connector, both of whom are threaded. And by the way, while we're talking about threaded connectors, if you see a knurl on the outside of a connector like this, it is not intended to be tightened by wrench. It's intended to be tightened by hand. And the impedance and the characteristics are intended to be measured with hand tightening. Now, we talked a little bit ago about SMAs and SMBs and SMCs. They, as you notice, have a hex nut, if you will, formed into the barrel, and they are intended to be tightened with a torque wrench. Finally, let's talk about the MMCX and the AMMC. Now, I want to treat these two together, and I'll show you examples of each in a minute. The MMCX was actually a European development intended to get around the patent on the UFL connector, the American and later filed in Europe patent on the UFL connector, which was filed in 1991. As I mentioned earlier, this patent has now lapsed due to failure to pay maintenance fees, and since then, Amphenol and other manufacturers have begun making an equivalent. In the case of the Amphenol case, it's called the Amphenol Micro Mini Coax, or AMMC. These are not the same connectors. Let me go back now to this board. The board uses UFL, or, if you prefer the Amphenol, the AMMC connectors. they look, don't know if this is going to focus, they are very tiny connectors, and they're intended to be very low profile. They were originally developed for use in RF situations where you had surface mount components on a board and you did not want what for those boards would be big old bulky SMA connector. So the UFL and later the AMMC biamphenol are connectors intended to be very low profile, but they are coaxial connectors. I'm sure you can't see that, but there actually is a coax inside, a pin inside that connector, and it mates to sockets like this. Now, one thing that I will point out with these kinds of connectors, they are not intended to be mated and remated like something like a TNC or an N connector or a BNC. These are made, the latter connectors are made to be connected and reconnected many times, usually hundreds of times, and they usually will last thousands of mating connections. But these little micro coaxial connectors are only intended to be mated 30 times. That's their rating. Now, some of them will last longer than that, but it's not something you're supposed to plug and unplug very much. It's supposed to be, you assemble the unit, you put in the cables, you connect them, and you leave it alone. So, I've showed you one kind, the UFL, which is used on this board. Let me show you a slightly different version of essentially the same thing, that is a micro miniature coax connector, in this case developed to a European standard. What you see here is a vector signal generator developed and marketed by Triarchy. I think they have discontinued this model, at least I haven't seen it for sale recently. It's a very capable USB. Notice it has the USB on one end and the N connector on the other. But on the back side, as well as on the end, are some connectors, some micro miniature coax connectors, but these are not UFL or AMMC connectors. These are MMCX. Let me put this in front of you again so that you can see the difference. These were developed under a European standard, the CECC 22000. They are essentially the same as the UFL. They work to about 6 gigahertz. They were developed, the original ones that were patented were developed or patented in 91, and then shortly thereafter the Europeans developed an equivalent, partly because they were very upset at the licensing terms that were being proposed by the holder of the UFL patent. So they developed basically a get around, if you will, to the patent, or a way to avoid the patent claims. And that was put in a standard, CECC, and published so that no one could patent it. And as a result, a lot of the European equipment, and later Asian and more recently American equipment, has the MMCX connectors. This is an MMCX connector. Notice that it looks like a little more robust version of the, let's compare the two here. Notice that one is a little more robust and therefore takes a little more space than the other. These I have found to be more reliable than these, especially if you mate and remove them more than a couple of times. And this is the type that fits the sockets that you see here. And if I can do this with one hand on camera, I'll show you how it clicks in place. And then you notice it's fairly robust. It holds pretty well. They are actually superior to these UFL connectors. But since they only go to 6 gigahertz, the same as the UFLs, and since the UFL patent has now expired, a lot of manufacturers are using the now essentially open source version of this, which is manufactured by not only Amphenol, but I think IPEX and other manufacturers. At any rate, these are MMCX connectors, and the alternative is AMMC. Why do I stress all of that? Because when you're ordering online, if you think you're getting MMCX connectors and you're not careful, you may be getting this one. Those are not compatible with each other. Even though they work to the same frequency specification, they are physically incompatible. So those are the basic connectors that I'm going to talk about. There are a plethora. If you're Chevy Chase, you know where that word comes from, or at least which movie it was used in. But these tend to be the most popular. Today, with miniature printed circuit boards with surface mount components, these are becoming much more popular. And the AMMC, because it's no longer subject to patent, is becoming probably the most popular connector if you don't have to mate and remove the connector very often. If you need something that is going to be removed and replaced fairly often, you really need to go with the SM series. And if you want a little bit of a blast from the past, you can go back to the old TNC, BNC, and N connectors. A lot of ham radio operators still use the UHF or shielded banana plug, because up to about the 2 meter band, which is around 145 or 144 to 148 megahertz actually, the old PL259s and SO239s work just fine. So I hope this has been useful information for those of you that are buying or using 50 ohm coaxial RF connectors. I think at this point I'm not going to do anything further along these lines, but I'm sure I'll be doing something. So stay tuned, stay safe, and have a nice day.